Greetings I bid to the GAs. My name is Samia and we are from Group 2. Following is the content of this presentation. To begin with, I'm going to present about the dynamic and static elastic properties of rocks. To begin with, elasticity is defined as this physical property of materials to return to their original shape after the stress is no longer applied. And they are generally described in terms of elastic moduli such as Young modulus and shear modulus, and in terms of elastic wave velocities such as compressional and shear wave velocities. Static moduli, for instance, are those that are directly measured from the deformational experiment analysis. That is, to assess the stress and strain using a core directly measuring. And dynamic moduli are those that are obtained or calculated from elastic wave velocities and density. But why is it relevant to study static and dynamic elastic properties? It is relevant. For instance, static moduli, they are often used in well-bore stability and in situ stress applications to evaluate, for instance, possibility of breakouts, elevated pole pressure, and tectonic stress distribution. And in this presentation, we'll be tackling Young modulus, the Poisson ratio, and Biot's coefficient. Static moduli in a laboratory core test is defined as the ratio of the actual stress change to the actual strain change produced when there is a change in the stress. And also it can be predicted from using empirical equations. For instance, we can see here an equation from porosity and also from free wave velocity. When the rock samples are not available, then we can use well-logged geophysical data to calculate the dynamic Young modulus. And we can see here that it can be estimated from density and VP and VS. And again, why is it important? It is important because Young modulus describes the capacity of a rock deformation or its stiffness, so that rocks with high Young modulus are representative of being less deformable or stiff, and that's why the initial part of a complete stress strain curve of the rock will be steep. However, for rocks with low Young modulus, that means more deformable rocks, the initial part of the complete stress strain curve will be gentle. And for instance, in this image, we can see that the sandstone has a much greater peak compressive stress and a larger Young modulus than those in mudstone. So therefore, the deformability of the rock can be assessed. Through the image on the right, we also can see that there is variations in Young modulus, such that rocks with high Young modulus are less deformable and rocks with low are more deformable. Also, in general, dynamic values of Young modulus are generally greater than those of static values, especially or it is easily seen when it comes to softer rocks such as shale as opposed to harder rocks when it comes to granite, for instance. And this is understood to be a cause of strain amplitude differences between static and the dynamic measurements. And next is the Poisson ratio, which is the ratio of a transverse strain corresponding to the actual strain of a material that is stressed along one axis only. And static Poisson ratio, it is a function of the porosity, of lithology, of confining stress, and pole pressure. And therefore, it is understood that Poisson ratio is porosity dependent, and this dependability is much or easily seen from dynamic Poisson ratio because it is theoretically a function of Vp over Vs. And for this reason, it is also understood that static Poisson ratio increases when porosity increases. Therefore, Poisson ratio differences among even similar lithologies can indicate also differences in porosity. And the dynamic ratio also in this image was not computed because the shear velocity was at the right one and not the wrong one. But we can see from the static Poisson ratio that between lithologies there will be differences in its porosities, or it is a reflection of the differences in its porosities. And lastly, Bayard's coefficient. Bayard's coefficient is defined as the ratio of the static pore space deformation to the total bulk volume change. And the static Bayard coefficient can be computed from the dry modulus and the matrix bulk modulus when they are available. But in the event that they are not available, the dynamic Bayard's coefficient can be computed from a derived or generated dynamic bulk modules. But it can also be computed from the well log seen from this equation. And an example is the Bayard's coefficient that was computed for the Boissier and the Heinisch-Waal shales in the image on the right. And we can see that on the left track, we can see the porosities from the well logs and the co-tests with the lithology column. However, when it comes to the middle track, we see the sonic log of the completional and the shared transit time, and on the right track we see the calculated Bayard coefficient, which was using that equation, this equation shown. And what can we conclude is that for unconsolidated or high porosity rocks, the Bayard's coefficient is close to 1, which is its upper limit. That means it's very high. However, laboratory measurements also demonstrate that underground rocks' Bayard coefficients value decrease with porosity from the values ranging from 1 at surface. We can see that these values change to values like 0.6 to 0.8 at porosities of 15 to 20% for carbonates and sandstones. And that is all from me. Thank you.
Thank you to my colleague Samia. Good afternoon, my name is Christabel. So proceeding, I would like to touch on some of the basics concerning inelastic properties. So as stated here, inelastic properties are the geomechanical parameters whereby its elastic limit can exceed and later result into rock deformation, or we call it rock failure. So there are a couple of factors that contribute to this condition. For instance, we have lithology type, we have microstructures, and also applied stresses. In fact, this is a very risky scenario, especially when it comes to drilling events, simply because they could lead to various well instability issues. So there are actually a few applications that we can conduct in order to study the rock strength. Here we have 4 examples of laboratory tests. So beginning with first, we have the uniaxial compression test. Basically, this determines the uniaxial compressive strength, or we call it UCS. Simple visualization here of how the stress acts upon the rock sample is we can see here in cylinder A. And next we have the uniaxial tensile test. This determines the capacity of the rock to resist the tensile stress. So here is example C. And next we have triaxial compression test. This is perhaps one of the most common tests that is conducted when we want to study the mechanical properties that covers a wide range of stress values. So we can see here it's visualized in cylinder E. And last but not least, we have polyaxial compression test. This is a test that simulates the in situ loading um, of rock scenarios in an actual field condition. So we can see here the example in F. So of course there are a lot of other methods and laboratory tests that we can conduct in order to further study the rock strength or its UCS. So now moving on, I would like to touch on some of the types of rock failures. So here we have 5 examples, beginning with first, splitting, that is example A. We also refer this to unconfined compression. And then we have shear failure, example B. This is expressed as a single plane of fractures, as you can see there. It usually has the inclined angle of less than 45 degrees. And then we have multiple shear fractures. This is the result of the increase in confining pressure with ductile rock. Next, we have tensile failure. You can see in example B, there is a clean separation there. And finally, it is the tensile failure induced by point load. So this is the effect of compression between the line of loads. So that is about the types of rock failures. Now, another important thing to note is that we can also evaluate rock strength, or its UCS, by applying empirical equations for different lithologies. So in the next slide, I will show you an example of how we apply these equations for sandstone and carbonate specifically, using two methods. First, it is the sonic velocity and transit time, and another is by using Young's modulus and porosity. So beginning with sandstone, the two equations here are one of the most common equations used. However, when we identify our sandstone to be poorly consolidated or a weak sandstone, which means that it has a high porosity of about 20%, we will use this formula instead. Whereas if you have a stronger sandstone, porosity of about 10%, this formula is applied. Lastly, when you have a more stronger and consolidated sandstone, porosity ranging of about 0.05 to 0.12, and UCS value of more than 80 megapascal, this formula is then applied. Now for carbonate, specifically for dolomite, this is the equations that are commonly used. However, there's also another approach to calculate the UCS is by using P wave as the input. Now, as mentioned earlier, another way to calculate UCS is by the input of Young's modulus and porosity. So similarly for sandstone, different equations are applied according to the characteristics of the rock itself. For instance, whether it's a weak sandstone, whether it is from a deep reservoir, or even in terms of its porosity, whether it is high or low. So these equations are applied accordingly. Now for carbonate, specifically for limestone, when we have the UCS values that range between 10 to 300 megapascals, we will use this formula instead. And also, as mentioned earlier, we also use porosity as the input. Now for limestone and dolomite, these are the empirical equations that are applied to calculate its UCS. Now before I end, here is an example of how we calculate UCS by adopting sonic velocity and transit time for sandstone lithology. So this is performed using the RockDoc software. We can see here in the figure on the right side, we have two logs. On the left is the sonic velocity measured, and then we also have the UCS calculated on the right side. So here we have the values to range between 7 and approximately 37. And by looking at these values, we can evaluate the rock strength, for instance, whether it is weak or strong, alongside getting information on its field characteristics as well as its associated lithologies. And this table here is an example of how we estimate this information. So overall, this example of the UCS calculated possibly falls under the weak and majorly under the medium strong category, for example. I believe that is all on the basics of inelastic properties in relation to its application as well as its types of rock failures. I shall now pass the floor to my colleague, Isa. Thank you.
Thank you, Christabel, for the insightful sharing on the inelastic properties. Now I will continue with another subtopic, pressure profile. What is a pressure profile? Pressure profile is a profile generated showing three different kinds of pressures, which include hydrostatic pressure, pore pressure, and lithostatic pressure, which is also known as overburden. Okay. So here is an example of a pressure profile taken from the book Applied Petroleum Geomechanics. Okay, so for example, here lies the hydrostatic pressure. Hydrostatic pressure is normal fluid pressure, which represents the pressure exerted from the vertical column of water. Next, you can see here is the pore pressure. Pore pressure is a parameter which holds a particular significance in the drilling and recovery stage. Usually, pore pressure is expressed in the form of gradient. There are several pore pressure techniques that are being used worldwide, but the most famous one is designed by Ben Eaton. Next is the overburden stress. Overburden stress can be defined as the sum of all pressures exerted by the overlying rocks and also the fluids. Why do we need to have this pressure profile? Pressure profile is important because it can allow the geoscientists to make prediction of how and when the original equilibrium state of the subsurface formation is being altered. Next, we can also know the location in the subsurface where different pressure levels are being subjected to the rocks. Moreover, by using the data from the pore pressure gradient, we can also determine how much mud is needed. Hence, we can provide appropriate mitigation measures. Hence, we will be able to reduce risk while drilling. How to generate pressure profile in rock dog? Okay, so there are three main steps to generate the pressure profile. The first one is to have the overburden pressure, hydrostatic pressure, and normal compaction trend to be calculated. Next, to predict the pore pressure by calculating its possible values. Lastly, to display the pressure profile by using these following selections. The first one is for the hydrostatic, we will choose the default. The electrostatic, the peak trend, we will not use the pressure. Lastly, for the pore pressure, we will use the Bowers option. After following the step-by-step procedures, we are now able to generate the pressure profile as what is shown here in this slide. Okay, so since we have the pressure profile and we can perform the pore pressure analysis. From this, we can have a better management of the reservoir. Hence, we can prevent any catastrophic events from happening due to overpressure or kick. That is all from me. Now I will pass to my friend Stephanie to explain more on the principal and effective stress.
Thank you, Isa. I'm Stephanie. I will talk about the principal and effective stress. So principal stress are the normal stresses, which is sigma 1, 2, 3, which is acting on the principal planes, as I shaded gray here. It is used to provide direct information on the maximum and minimum values of the normal stress components. Stress elements is rotated such that the shear stresses become zero, which I will show in the next slide of the Mohs circles. As a result, the highest value is sigma 1 and the lowest value is sigma 3. These are the few examples in industry that applying the principal stress. So this is the 2D Mohs circle diagram where sigma 1 is higher value than sigma 3 when the shear stress are 0. So to define the effective stress is equal to total stress minus with the product of Biot's coefficient and pore pressure. So these are the formula of the effective stress. So here is the total stress, where this is the formula of the total stress. And also the alpha, based on Terzaki's effective law, alpha is equal to 1, means that the value must be less than 1. And for pore pressure predictions, for the next slide, I will show few example of methods to predict the pore pressure. There are few other methods that I found in the books and paper for pore pressure predictions. However, I will share only these three just to see the differentiation. First is Holbrook, Eaton, second, and the third one is Bowers. Basically, Holbrook pore pressure, it doesn't require the normal compaction train. I also show some example case study that using the Holbrook pore pressure. However, for Eaton and Bowers pore pressure, both need the normal compaction train, and both these methods are using seismic velocity, require the use of seismic velocity. However, for lab, we are using the Bowers pore pressure. Bowers pore pressure, which is based on effective stress approach, which can be used, which is based on the formula in the previous slide that I showed. For the next slide, I will show the result of the lab which are using the Bowers pore pressure. So here is the result of pore prediction during lab by applying the Bowers pore prediction method. So here's the workflow that for the lab during lab. First, we have to calculate the vertical traces by input raw data, and after that we have to calculate the NCT but input the VP data. So in conclusion, Eaton method is more directly applicable and relatively quick. On the other hand, Bowers method has higher sensitivity in population estimation from seismic velocities. Now I pass the floor to Afika for the seismic attribute for fractures of fault identification.
My name is Nurul Afika and I will be presenting about the application of seismic attributes to identify fractures or faults. Well, by definition, seismic attribute is a quantity extracted from seismic data that can be computed in order to enhance the information in raw seismic image. Each of these attributes provides different information from seismic data. For example, RMS amplitude attribute can be a hydrocarbon indicator where it highlights bright spots area. It is proven that the application of attribute leads to a better interpretation. In characterizing faults or fractures particularly, many researchers in the past have utilized discontinuity attributes, where it can detect displacements as it measures the similarity or dissimilarity between seismic traces. Examples of discontinuity attributes are curvature, coherence, and deep azimuth and magnitude. Nevertheless, there are more viable options in choosing the right attributes to delineate structural features on our study area. I would like to demonstrate the outcomes of several attributes that have been applied on the raw seismic data and how it enhances the presence of faults and fractures. As you can see on the slide, at the center image is the original seismic data where we are able to trace some discontinuities of seismic reflectors and interpreted the presence of one normal fault which dips in the southeast direction. Now, by applying few attributes at the exact same inline section, more distinct reflectors are seen. Therefore, we are able to locate and characterize more faults and fractures, if any. Firstly, we apply 3D edge enhancement attribute, where it is an edge detection improving attribute which filters along planes in three-dimensional direction. From here, we can observe that the reflectors are more prominent, which makes it easier to trace the discontinuities and different stratigraphic layers. There are 3 interpreted normal faults in this area which dip in the similar direction. Other than that, we also apply amplitude contrast attribute, where we can obtain a higher resolution image as compared to the original seismic data. The algorithm of this attribute is based on a Sobel filter which conducts a 2D spatial gradient measurement on an image, which emphasizes on regions of high spatial frequency that corresponds to edges within the image. From this attribute, we are also able to trace few discontinuities, layers of discontinuities, and locate 2 presence of normal faults, as you can see on this image. Next, we also applied the traditional attribute to delineate structural features, which is the structural smoothing attribute, where it works by generally smoothing the area and increase the signal to noise ratio for structural interpretation. By using this attribute, we are able to detect discontinuities and 2 normal faults. However, the section in the southwest part are hardly distinguished. In this part are hardly distinguished due to the presence of noise. Lastly, we applied variance, which is also able to reveal discontinuities either related to the stratigraphic determinations or structural lineaments. Clear reflectors are detected in the southern part of the area, indicating the presence of 2 normal faults dipping in southeast direction. However, structural smoothing and variance attributes show less distinct reflectors as compared to the 3D edge enhancement and amplitude contrast attributes, because they are designed to suppress signal to noise ratio in the original data, therefore losing some fine scale data and not every discontinuities, especially the small scale faults, can be identified. Therefore, it is proven that the application of attribute can reveal discontinuity of seismic traces. Therefore, we are able to characterize and identify the presence of faults in our study area. We have reached to the end of our presentation, where we have discussed thoroughly 5 different topics. I would like to summarize each of the topic on a short note. Firstly, static and dynamic elastic properties are useful in order to evaluate the deformability of rock and correlate it to its petrophysical properties. Secondly, in inelastic properties, it is very important to first study the rock strength in a reservoir by performing laboratory tests or empirical calculation before conducting any major drilling event. Thirdly, pressure profile is important in order to perform pressure analysis, as it can give information on mud weight as well as the location of overpressure and underpressure in the subsurface. Next, principal and effective stress can be used in engineering problems, as the practical interests are effectively in two-dimensional direction. Lastly, the application of seismic attributes is the best approach to improve the quality of seismic image, therefore leading to a better interpretations of faults and fractures. With that, I would like to end the presentation. Thank you for listening and have a nice day.